So I have great pleasure in introducing the first speaker. I'll come in and introduce the second speaker later. Dharmendra Moda is an IBM fellow. He's my colleague. I've known him forever. He works on many topics, but the talk will be on brain-inspired computing. He's also the IBM chief scientist for that topic. He has worked on storage and various areas. He's a PhD from UC San Diego. Come on over. He's also a distinguished alumnus of IIT Bombay. Dharmendra, let's see. We will load your thing. Okay, you can start saying stuff.
Sure. Good afternoon.
So human brain is capable of incredible X. Ooh, echo now. The technology, so you can tell why today's technology or computers are no match for the human brain. I'll just come down and talk with you. Okay. So today's computers, I contend, are just calculators when compared to the human brain. So you know what? I'm complaining about the technology, but I need a wireless clicker, so I have to go back up. Those of you who are Indian know the meaning of pradakshina, right? Okay, so the first step to building a brain-inspired computing is to begin to understand the anatomy and physiology of the brain. And we started by mapping out the largest long-distance wiring diagram in the primate brain. What you see around the periphery are 383 brain regions in what's called cortex and subcortex. And the wires are 6,602. So this data was compiled by pulling together 410 studies over 6 decades. And it tells us how the communication patterns of the brain are. Now, taking this data, we built a mathematical simulation of the brain. The purpose was not to emulate the brain, but to understand 7 variables: computation, communication, memory, power, area, speed, and cost. So simulation at the scale of 100 trillion synapses, human scale, required 96 racks of Blue Gene Q Sequoia supercomputer, 1.5 million processors, 1.5 petabytes of main memory, 6.3 million threads. And guess what? Yet, the simulation ran 1,500 times slower than real time. So a hypothetical supercomputer with today's architecture to run 100 trillion synapses would consume the power equivalent of a nuclear power plant, 12 gigawatts. In contrast, the human brain occupies volume comparable to a large bottle of soda and the power of a dim light bulb. So if you are looking for an area in which technology can make an impact, here's a billion-fold disparity. So to bridge this gap, over the period of about a decade, we have been developing a completely new computer architecture. A computer architecture that breaks path with a 70-year-old architecture that has been with us since ENIAC, 1946, when John von Neumann wrote down the basic principles. The new architecture that we invented is parallel, modular, clock-free, event-driven, scalable, fault-tolerant, non-von Neumann, And to embody this architecture, we developed this chip. It's called True North. This chip is composed of 4,096 tiny little neural networks, each called a neural core. Each core is 256 neurons, 256 inputs, exons, and 256 square, which is 64,000 connections. And 4,096 of them together make up 1 million neurons, 256 million synapses, 5.4 billion transistors. This is literally a supercomputer the size of a postage stamp. But what's beautiful is that it consumes the power of a hearing aid battery. So this thermal shot tells you the innovation embodied in here. On this side is the True North chip in a socket, and on that side is an FPGA, which is just passing input. And you can see the coolness. The power density of the chip, which is the amount of heat emitted per unit area, is 20 milliwatts per square centimeter. The power density of a modern CPU is 100 watts per square centimeter. You're talking about a 5,000x improvement in a very important metric. So now taking the True North chip as the foundation, we built a single chip board. So this board is our development workhorse. We have hundreds of these in production now. It's the size of a palm, and it's been distributed very widely. And then we took 16 of these boards and tiled them together into a scale-out system. And this system has been recently shipped to US government, Air Force research, as well as Army research next. This system has 16 million neurons, 4 billion synapses. That's roughly the same number as in a small mammal, like a tree shrew. And then, very recently, just a few weeks back, we delivered a scale-up system to Lawrence Livermore National Lab, just about 40 miles from here. This is very unique because it consists of 16 True North chips tiled in a 4x4 array with no interface circuitry between the chips. The chips directly talk to one another like the human brain and scale up homogeneously. Okay? So now I told you about a new chip, I told you about the new systems, but you cannot rewrite the very foundations of computing and expect to compile a language based on Fortran, which is what we've been doing, to it. So we created a completely different end-to-end programming workflow consisting of a new simulator, consisting of a new programming language, deep learning tools, extremely easy to use. And to give you an example of what you can do with it, here are two videos, one from a stationary camera, another from a moving camera, and the chip and the systems can do 30 frames per second, 3-color classification in real time, consuming milliwatts of power. Now, most of you may have heard of deep learning. It is very easy now, we have shown, to map neural networks learned using deep techniques onto the chip. And so here's a classic data set called CIFAR, which consists of several classes, airplane, bird, car, so forth. And we can do state-of-the-art recognition on the chip using this data set as well as the training. One more example, recognizing corporate logos, 32 logos collected by European students. They're mostly beer. German traffic signs, about, I think, if I remember, 43 classes, 32 by 32 pixels, 3-color. CIFAR 100 classes, many common objects, which you can sort of guide your eye all the way from Apple to car and so forth. And then this doesn't just work on video or images, but you can also apply it to audio data. And here's actually, you can't hear the sound, but it's a 39-class phoneme classification problem, But again, state-of-the-art accuracy. And what's amazing about all these data sets that I showed you is that each one of the data sets is performing its classification at greater than 5,000 frames per second per watt. This is unprecedented energy, speed, efficiency by going to a brain-inspired paradigm. And now what we have done is we have taken our architecture, our system, our programming, and we have jokingly created a new university called the Synapse University. Of course, this is an endearing term. But what it is a training curriculum, which we have been inviting people to IBM and training them. And now this training curriculum is in the hands of more than 100 developers at 30 plus universities, national labs, government agencies, as well as corporate labs. And as we look to the future, I envision building, within foreseeable future, a brain in a box. Literally 10 billion neurons in a shoebox consuming less than 1 kilowatt of power. So with that, I thank you for inviting me here, Mohan, and thank you for your attention. Thank you.
We are going to now switch to his presentation because we are running late already. Thank you very much. Appreciate that. So the next speaker will be Professor Chris Ray from Stanford, another friend of mine, and I've heard him give wonderful talks in various places. Chris recently moved to Stanford from University of Wisconsin, where he had started working after his PhD from University of Washington. He has got a number of awards, including the Best PhD Dissertation Award, and most recently, the most exciting one, I guess, would be the MacArthur Foundation Genius Grant. So you go read his resume, and you will see all sorts of very nice things. And his presentation will be this. He wanted to give a newer version of it, but talk of compatibility problems and all that. So
Thanks, Mohan. Oh, yeah, looks pretty risky. Okay. Thanks so much. It's a pleasure to be here today. Very much appreciate the invitation. And I was asked to talk about this topic, will AI make humans obsolete? I don't know if you've ever heard this adage called Betteridge's Law. It says that any headline that ends with a question mark can be firmly answered with a no. So I'm not going to talk about why AI is making humans obsolete, but I am going to tell you why people are so excited about AI and machine learning. And of course, I'm going to tell you about it via my own work. Okay? So we've been working on this project called Deep Dive for a number of years, and I was excited to hear in the last panel someone use the phrase dark data. This is some phrase that we've been using for a couple of years now. What dark data refers to is that great mass of data that goes unused inside organizations. This is the scientific articles that they're publishing. These are Word docs. These are sensors, images, all that data that gets stored and then is never used. And so Deep Dive started with this mission about 4 or 5 years ago to figure out how do we exploit that dark data, take that dark data and put it into a structured kind of setting like a SQL database. Now, what's been exciting about this project and a couple of others is that we've actually been able to take these pipelines where right now humans are employed, and I'll show you one place where humans are employed, to read that dark data and put it into a structured form. But with machines, we've been able to actually replicate those pipelines and, of course, scale them up and actually do it with higher quality than the human volunteers. So what I want to get across in this talk is, in what sense are these things higher quality, and why are we so excited about these new kinds of almost cognitive tasks where machines seem like they can be a replacement for humans? But before I get into that, I want to give you a story just to motivate how this work came into being. So our story begins in kind of an unexpected place, perhaps. Isaac Newton, probably not what you thought I was going to start with. But Isaac Newton, if you're not aware of him, co-inventor of the calculus, general intellectual badass. When Newton had his great discoveries, what did he do? Well, he set down a text. This is one original copy of such a text. And it turns out that actually Newton was not alone. Like each one of us today, when we have some minor breakthrough, not as big as Newtonian mechanics, or we understand something about our organization or the world around us, we write a report. And when those reports are published, they go to places like this. So maybe 15 years ago, they would go to something that looks like this. This is a library, and people used to store books there, okay? Now, about 15 years ago, this all changed because everything went online. So actually, you can go into, Google Books, type Principia Mathematica, and you get back a PDF version, an English translation in this case, of the document you're looking for. Okay? So why this is relevant to us and what we're going to talk about here is that the world's scientific knowledge, and indeed much of the world's knowledge, is actually accessible in a way like never before. If you know what you're looking for, you know the DOI, you know the keywords, you can go out there and get that information. And that makes this an incredibly exciting time, and this is why all that dark data has been generated. For years now, companies are acquiring this data, storing it in their data lakes, but there's still a problem. Okay? And the problem is shown by our friend here, right, carrying this huge stack of books. Now, one of our friend's two problems is easy. Storing the data is something that for scientific articles, we can do pretty easily. You can fit all the scientific articles you'd ever want to read in your lifetime on your phone now. I think my latest phone has 128 gigs of storage. So this storage is not a problem. The problem is that for even the narrowest of scientific questions, it requires reading a huge volume of data that even a very well-funded army of people simply can't plow through. So to give you one scary stat, every year there are 1 million new articles published on PubMed. This is medical knowledge that's potentially useful to you if you want to go to the hospital and you don't want to go there, but you'd like a cure. It could be buried somewhere in that 1 million articles. But no one's reading all of those articles, and definitely not your physician. So the world's scientific knowledge is accessible in a way like never before. If you know what you want, you can get it, but it's not readable. It's not something you can pull together and have at your fingertips. And so that's the kind of problem that we wanted to solve in these dark data problems. Now worse, this is motivated by a bunch of strange problems from all over the place. We started in science, so we started working on things like climate and biodiversity. So that's what I'll share with you today. But also this crops up in health, and increasingly at Stanford I started collaborating with friends in Stanford Hospital. I saw Nigam Shah around here earlier. There's a bunch of interesting work going on that's basically taking all the literature that's out there about genomics and genetic conditions and all the rest, drug interactions with Russ Altman, boiling it down and trying to make sure it's at your physician's fingertips when you need it. We've also been doing a bunch of work in financial markets as well, and I'm happy to talk about that offline. So let me tell you a little bit about this climate and biodiversity thing we've been doing, because it's the first thing that we actually built. So we asked this very naive sounding question. Could we build a machine to read for us and do this reading and summarization problem? Okay. Now I don't mean it in some kind of singularity way, like it's not going to read and feel things. I just mean that it's going to take in the same PDFs that the humans were reading and then produce the same structured database. Okay? So to show you what I mean by reading, let me illustrate with one example. I don't expect you to read this document, but it'll become clear what I mean by reading through this example. So the information that the scientist would like to collect is actually inside tables that look like this, okay, and in the text. So we'd like to be able to extract this fact that in this region called Obora, we actually found this thing called Moravalomacryas. Now this is a genus of cockroach. If you love cockroaches, this is hot stuff, okay? Now, I don't actually like cockroaches, but I can imagine that someone who studies the climate probably does. They probably want to know everywhere one of these little cockroaches was found and in what region and in what time. Now, if you think a little bit about how you would have to write a script, like a Python script, to do this extraction, think about all the low-level stuff you would have to do. A little bit of image processing to find where the lines are, understanding that there's localities is kind of a reference to location here, that the first part of the word is a genus, not the whole thing is a genus and a species together. You'd have to write a series of complicated scripts to even get out the right pair that we're looking at here. Even if you solve all that low-level stuff, you still have another problem. In the data set we were looking at, there were over 40 different oboras that they had distinguished between as locations. And by looking at the table, we had no idea to which one we were referring. So now here, we actually have to go into the text. This is the body of the article, not the caption. And we get what seems to be very lucky. The obora site is situated, blah, 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 and the GPS coordinates. So if we could go into the body of the article and actually read and extract this information and somehow resolve it to the table and do that resolution automatically, we could do what people do and put this data actually into a database. And that's what I mean by reading. A person would do this by reading the text and going back and forth. And we want to build a machine that's able to do the same thing with very high quality. Okay? So this isn't vaporware. We actually built something that did this for paleobiology, and as I'll share a couple of other domains. This thing called Paleo Deep Dive with some geologists and some other folks, including my student So, who just told me that he's going to go be a professor at ETH. So we're very proud of him. Anyway. So the goal of this system was very simple. These biologists want to know where every fossil was found and in what time period it was found. So they've taken a bunch of PDFs like this, and they produce a database. And their database is actually a standard SQL Postgres database. They define the schema. And to a first approximation, what we want to do is replace the people who are reading the text and putting it into a database. And by the way, 2 continuous person decades were spent on this process that I'm going to describe. We want to replace it with a machine. And that machine's going to take into a first approximation some text and some dictionaries, and it's going to use statistical inference to try and figure out the most likely database that's on the right-hand side. Now, I won't bore you with the details. The things that we spend our nerd lives on are basically trying to solve the underlying statistical inference problem before the heat death of the universe. But basically what we do is every one of those little choices that we were making in your script, we now make a random variable. Okay? And so we try and estimate all of those choices. Once we see all of the data, what is the most likely extraction pipeline that you could have written to create the database that the human would have created? Okay? No one cares about the nerd details. What you care about is whether or not it works. Okay? So the way we evaluated it was as follows. There's this database called PaleoDB, 2 continuous person decades, hundreds of volunteers, reading papers, postdocs and PIs, people with PhDs, reading the text, putting it into a database. Okay? Now, we built the same thing on top of this other framework. And when we turned it on, we were able to read 10x more documents than the humans had read in their 13 and now 15 years of building this thing. Okay? Within those 10x more documents, which isn't surprising, right? We're a machine, they're people, we'll read a lot more data. Within those 10x more documents, we got 100-fold more extractions. Okay? So that means that people weren't being very systematic as they were going through these documents, and they were leaving a ton of these facts or extractions on the ground, which were basically lost to the ages. Okay? The second measure of quality is how accurate are the facts that we actually put into the database. But the first question we really asked is how accurate are the volunteers? So we went and we assessed over a period of about 2 years, how accurate are volunteers when they add information to this database? And it turns out their accuracy, as rated by experts, is only about 84%. So what happens in that 16% where they go wrong? And it turns out there's a very interesting class of error. The interesting class of error goes as follows. They read the document, they say, I know that this location is now called by a new name, not the old name. It's no longer Obora, it's the Obora Shale Formation, and I'm going to put the new name, not the old name, in the database. When they're right, this is good. They've used their background knowledge to help you put higher quality data in your database. When they're wrong, this is catastrophic, because now this database takes 2 person decades to rerun. There's no way you're going to find and track down these errors. But even when they're right, it's not great. And the reason it's not great is one person who's doing the extraction is doing it one way, and another who may lack the background knowledge is doing it in an entirely different way. And so as a result, your database isn't standardized in any kind of reasonable way. Now, we run in 45 minutes on this application. If you don't like the way we're normalizing, simply redo it, and then you'll be ready to go. So not surprisingly, our accuracy is actually higher. And this is a cherry-picked number. Of course, it's something that we're substantially better than the others on. But actually, on all the predicates that they defined, we were statistically no worse. And you can look in the Nature write-up to see what we looked like. Okay? Now, we've applied this to things like the tree of life and drug repurposing and genomics. But I wanted to share one very unexpected application that we worked on, which is human trafficking. So about 2 years ago, DARPA came to me and said, would you like to work on human trafficking? And of course, I said, for or against. And they said, against. I was like, oh, okay, good, I can do that. Anyway, no, just kidding. So they asked us to work on this, and I'll give you basically the short version. It turns out that prostitution, like everything else in the world, has gone online. So people are publishing these small articles that look like Craigslist-style postings and offering sexual services. And the idea was that if we could extract from those things the prices and the service being offered and a host of things that would basically go into a pricing model, we could identify individuals who are trafficked because they would have an ad that would be priced slightly lower than the competition, all other things being equal. Okay? So we actually did this. It turns out that it's actually very difficult to extract this information from text because it turns out that scientific articles want to be clear and sex ads less clear, perhaps. And it also turns out that they take countermeasures against us once we were deployed. But the point is that this extraction technology actually seems to have interesting societal impact and interesting economic impact as well. And so this is now publicly in use at a bunch of different DA offices and other places. And I can't really talk in too much detail about exactly what we did. I will give one little plug that a startup has started about a year ago. That's Mike Caffarella. He's the co-founder of Hadoop, and he's also the CEO of our company. And we have a bunch of different engagements in broadly the financial services and law enforcement, intelligence, and defense. Okay? So to conclude, I think I'm out of time. There are many applications, thanks Mohan, there are many applications in which computers can do human things. That doesn't make them humans, and it doesn't mean everyone's going to be out of a job. It's exciting enough that they can actually do something with human-like accuracy that's more of a cognitive task. Not a machine task where they're drilling something in, but something that looks and smells and feels like a cognitive task. Thanks so much for your time.